Welcome to Learning Module 2, which is focused on data visualization. As we have discussed in the Learning Module 1, this is critical to the overall data-driven decision-making process. Before we start organizing and summarizing data, before we look into trying to infer with confidence, one of the most important aspects is to try and visualize and see if the data is able to tell a story or not. And so before we look into the various ways of visualizing data, it is oftentimes important to recap um, the idea of data types and measurement levels, because um, that will help us realize how, depending on data type, you can do a certain form of visualization versus a different form based off of the data type. And this applies to any kind of software that you're using. In fact, in many software, they will eventually figure out if the data is qualitative versus quantitative. And depending on what that data is, it will be grouped in a certain format. And we will learn this in the context of Excel, in the context of R, as well as in Tableau. It's pretty fascinating, but for each of these software, they eventually need to know the kind of data. Sometimes it's very clearly showcased in the data type itself. So if you have data that is very clearly articulated, let's say as male, female, and so on and so forth. So these are a bunch of characters, and that's how the data type is definitely qualitative. It's a nominal kind of data. It's categorical. As opposed to that, if it's numeric data, depending on the kind of numbers that are in place. If it is in decimal, in most cases, it's continuous data. And so that's quantitative. If it is um, discrete numbers, then it can also be ordinal data or interval data. So it again depends on the context, but in most of these cases, the software will figure it out. And so when you are charting that data, when you are visualizing that data, the way you visualize data depends on the kind of data you're working with. So in this specific video, the first video of Learning Module 2, we will start looking typically at categorical data. And categorical data modeling has its own advantages. First and foremost, it's much more simpler, it's easier. There are only a very few set buckets within which the data is present. If this is the data on sex of the individual whose data has been collected, then it's male or female. If this data is on a certain level of education, while the student is at the university, then the student can be a freshman, a sophomore, a junior, or a senior, any one of those four. And so based off of that, what you can do is you can visualize the data set in one of two forms. Either you can find a distinct count of each of these buckets. So how many males are in the data set? How many females are in the data set? How many freshmen? How many sophomores? How many juniors? How many seniors? And you can subgroup as well. How many freshmen are females? How many juniors are males? How many sophomores are females, and so on and so forth. So there are multiple ways to count the data to get a feel of what the data set includes or the demographics within the data set. And the other way is to look into how the categories seem to differ or not by a certain measurable. And we'll talk about this as we go in the flow of this video. But as an example, if I'm trying to compare between males and females in terms of grades in the class, just by the data set that is at hand, which one seems to fare better? If there is a course that is available for freshmen, sophomores, juniors, and seniors to take in the university, example is the foundation study class, is there a certain group of individuals who typically would do better in the class? Okay, and again, these are all smell tests. And that's why I used the term seem to. You cannot yet infer with confidence. You have not used a statistical technique yet. It's essentially trying to see what the data is suggesting. It's a suggestion at this point of time. So categorical data also helps to surface the subplots of the underlying problem. The underlying problem may be to understand how your grades are interspersed. When you do meta-analysis of that underlying problem, a sub-problem could be if males and females differ in the context of grades. A sub-problem could be, are female seniors better at this subject in terms of grasping the subject based on their grades, as opposed to, let's say, male juniors, even though their grades seem to be very similar based off of this data set? Is there a real difference? Okay, so all of those questions would eventually be answered when you do the statistical analysis. But to set the stage, this is what the data set does to you. This is where the visualization kind of gives you an understanding of which way it is headed. So that's where managing categorical data becomes extremely important. So let's look into a few ways of charting categorical data. Okay, so this is a specific example where the top 10 causes of death in the United States in 2001 have been charted. And so what you see here is the rank in terms of causes of death. So heart disease has the number 1 rank. It has 700,000 counts of death, followed by cancer, followed by cerebrovascular, followed by chronic respiratory, and so on and so forth. But here is something I want you guys to take away. This is not the data set. It is an analysis of the data set. The original data set, let's say, is of 2.4 million people whose data, healthcare data, has been taken into consideration. And 2.4 million deaths in the US in 2001 from all possible causes. And then for each of those 2.4 million data points or rows of information, there is a certain cause of death. So of those 2.4 million deaths, 700,000 is attributed to heart disease. 553,000 is attributed to cancer. 163,000 is attributed to cerebrovascular. 629,000 is attributed to all other causes apart from the top 10. And so when you have that, now you can figure out that your heart disease corresponds to 29% of your total deaths being 2.4 million. Cancer corresponds to 23% of total deaths, and so on and so forth. So there is a distinct difference between these final two columns. The first one talks about percent of top 10s. The second one talks about percent of total deaths. And they are different. The percent of top 10s essentially creates a percentage based off of the total count of the top 10 only. So naturally, your heart disease percent of top 10s is much higher than the heart disease percent of total deaths. Here, the underlying population is 2.4 million. Here, the underlying population is only the sum of the top 10 deaths. And so we have to understand, when we are reporting data, what is it that we are using in the reporting process. And so once you have the tabulation, now you can actually create what we define as bar charts. Okay, so these are also called bar charts, and we will discuss how we can come up with bar charts in the next video. How to design bar charts and so on and so forth. We'll talk about that in the next video. So this is called a bar chart. So this bar chart basically provides you the top 10 causes of deaths in the US in 2001. The takeaway from this specific slide is that when you design your bar chart, always make sure that it is sorted by rank. Okay, it's so much easier to analyze because right away without looking at the numbers, I can look at this and say, okay, heart disease is the biggest mover and shaker of causes of death, followed by cancer, and so on and so forth. Here it's much more haphazard. You have to now look into cancer. Oh, cancer is so much higher than the others. Oh, I have heart disease here. Oh, maybe heart disease is a little bit more. You don't want a viewer to work harder than they need to. And therefore, the upper approach is the easiest approach to ensure that a viewer has consistent understanding of how the causes of death continually go decreasing as you go from a left to a right. Okay, and this can very well be done in a different plane. So I can design a plane and define my bar charts in this form. It still solves the same purpose. Okay, it just depends on how you want to represent that data. So that's one way of representing the data. The other way is what we define as a pie chart. Okay, so each slice represents a piece of one whole. The size of the slice depends on what percent of the whole the category represents. So percent of people dying from top 10 causes. Okay, so this represents top 10 causes. And that should be the biggest takeaway before even you start looking into understanding what those percents mean. You have to understand the underlying condition, which is top 10 causes. That is different from, let's say, looking at percentage of deaths from all the causes. As you can see, those numbers change, and you have something called other that is also clearly articulated in this section. Okay, so that is extremely important in the context of labeling. Okay, make sure that your labels match the data and make sure that all your percents add up to 100. So when you are looking into visualizing categorical data with measurables, if you try to understand the summary meaning the counts, this is where bar charts and pie charts come in. And later on, in this set of 2 weeks, you will read some Harvard Business Review articles that will give you some more insights on how to represent a chart, where a pie chart is needed, where is it not needed. So a great example is if I have to showcase the data set in the form that it is this way, is it a pie chart versus is it a bar chart in which I should represent my data? I mean, pie chart looks extremely convincing, lucrative, um, very colorful. But to grasp the overall idea in a simplistic way, a bar chart is always better than a pie chart under these circumstances. So that's where the idea of a summary comes in. So if I'm looking into, let's say, males and females, I can basically do a bar chart of counts, which gives me a synopsis of the fact that I have more females than males in a certain data set. And so this can be done in a pie chart as well. The pie chart will show something that is very similar. This will be females, this will be males. It can provide the certain percent for both of these chunks, but they all tell the same story. So that's the idea in terms of summary. This is count or frequency. It can also provide you summary in the context of another measure. So this could very well be a male versus female in terms of their average grade. Okay, where from the data set, I am capturing average grades, and it turns out that On an average, the females register a better grade than the males. This can be a data set of males versus females capturing average salary. And it turns out that males on an average capture a higher salary than females. And that is basically what the data set is capturing for you. So this is also a bar chart. This is also a bar chart. This is a pie chart. So they all capture what we define as summary, be it in the context of count, how many of those clusters are present, or a summary data meaning an average value. It's not giving every single data point of salary for the males or every single data point of salary for the females. That is not what is captured in a bar chart. It gives you a magnitude at the end of the day. That can be of count, that can be of a certain measure corresponding to that specific cluster or classification, and it has to be a summary measure. So it can be an average, it can be a median, and so on and so forth. And we'll talk about summary measures later on in this learning module. So that's one way of visualizing categorical data. What if I want to get some more information, let's say, on grades between males and females? That goes beyond just a summary measure or the average. Can I get an understanding of the dispersion of data in terms of grades for males and females? Dispersion meaning variability of data. Can I get an understanding of what the maximum value or the maximum grade for females is, what the maximum grade for males is, what's the minimum grade? Are there outliers in the process? So when you want to do detailed comparison of measurables, especially in the context of categorical data, another way of looking into that is what we define as a box plot. And we will look into this in much more detail later on in our learning module, in this specific learning module. And let's say this is males and this is females. And so as you can see, if you are looking at the lower level, they are very similar. The higher level is where the females have scored much higher. There may be a higher outlier which has actually moved the overall mean or the average grade higher than the males. And we'll talk about what outliers mean in the context of summary data again later on in this learning module. But this approach provides you a lot more than just a summary measure. It gives you how much of a stretch or um, diversity is there in the grades within a certain characteristic. That's what variability is about. How much of dispersion is there? Are there specific outliers? Um, where the median stands in terms of the data set. Okay, what's the true way of representing that data? It provides you a lot more than just a summary measure. And that's where detailed comparisons, especially when it comes to categorical clusters, are best done using what we define as box plots. It also helps you identify if what we define as an outlier is a true outlier or not. So that's one way of looking into it. Okay. The third way of using or visualizing categorical data is when you have two sets of categorical variables. Okay, so imagine that I have categorical variables by sex, which is male versus female, and categorical variables in terms of full-time employee who works full-time 40 hours a week and then comes to my class. Okay, so this is a yes versus no. And so now what I have defined here is what we call a two-way table. And so the two-way table again can be done in two forms. I can look at this as count. Okay, so I can specifically count the males in my class who work full-time, which is this specific quadrant. I can specifically count the females in my class who do not work full-time, who may be full-time students working as GAs, and that would be the count in that quadrant. And I can define the same exact thing in the context of measurables. I can actually have this as grades, okay? And this has to be, again, summary measures, okay? So average grade of females who are not full-time employees, average grade of males who are full-time employees. So all of that can be captured using what we define as two-way tables. Okay, you can do counts or you can do measures, but this has to be summary measures. The only way you can go beyond summary measures is using something called a box plot. So very broadly, these are the three different ways in which categorical data can be manipulated, can be visualized. And so there are also scatter plots depending on continuous data that you are trying to manage based off of multiple clusters or groups. So if you actually look at this entire data set, okay, and we will talk about relationships, okay, this entire data set, if you look at that as a whole, it may look like a positive relationship. As negative species go up, your number of exotic species, as native species go up, your number of exotic species also go up eventually. Imagine that this is some kind of a relationship that we are trying to set here. And so um, on face value, it may actually look like it's a positive relationship. It's a plus relationship, like we discussed in our conceptual model, right? So this is your X variable, this is your Y variable, right? But if you aggregate the data properly and look into the bands of data, and let's say these are 5 different bands or clusters based off of some categorical importance or significance, if you look into each of those categories, now the direction of association is completely changed. As you can see, the direction of association is going in a negative direction. As you move this direction, your number of exotic species continues decreasing. So as your native species increases, your exotic species actually decrease for each of those clusters. And therefore, plotting different habitats in different colors allows us to make that important distinction. This is where visibility is at its best, when you are able to showcase that data properly. This is where clustering and categorical variables really help in understanding if there is a common pattern across all of those clusters. As I said before, when the explanatory variable is categorical, you cannot make a scatter plot, but you can compare the different categories side by side on the same graph. Okay, and so this is where if you're looking into total income in terms of dollars based off of somebody who is not a high school graduate versus who is a high school graduate, somebody who has done some college, let's say an associate's degree, somebody who has done a bachelor's degree, or somebody who has been going through an advanced degree. This is how your total income increases. And as you can see, there is a very high number at the higher end, which will naturally increase the overall average salary for somebody with an advanced degree. So comparison of income for different education levels. This is not a positive association because education is not quantitative. Okay, so you're just looking into the level of education. Therefore, you can't make an association like we were able to do in the previous category. And then the bar charts and pie charts, they summarize each categorical variable independently. But the two-way table actually describes the relationship between both kinds of categorical variables. So the cells of a two-way table represent the intersection of a given level of one categorical factor and a given level of the other categorical factor, as we just discussed. So as an example, if you can use education as the row variable here, okay? So did not complete high school, completed high school, college 1 to 3 years, and college 4 or more years. Let's suppose those are the broad categorization of the education variable. And then age group becomes the column variable. So between 25 to 34 is one age group, 35 to 54 is another, and 55 and over is the third one. So now for each cell, we can compute a proportion by dividing the cell entry by the total sample size. The collection of these proportions would then help us understand the likelihood at the intersection of those two variables. And so for a certain data set, if there are 4,459 people who are between the age of 25 to 34 and who did not complete high school, what is the likelihood of finding that kind of people in the data set? And that likelihood would be this number, 4,459, divided by the sum of all of these numbers taken together, which is the entire data set. And we can do the same exact thing for all of these others in terms of where the intersection happens. That intersection defines the characteristic of a certain level from both the variables. So if I'm looking at 11,125 data points, those are data points of people who are 55 and over and who have been to college for at least up to between 1 and 3 years. Okay, and so that then gives me a likelihood of occurrence for characteristics of people who have been to college between 1 and 3 years and who are 55 years and over. So that's a very, very powerful takeaway from the data set. And again, this one represents only in the context of count. I could basically do this in terms of, let's say, summary grade. If this is the data set that also represents students who have taken a class. And I can actually say what the average grade would be for somebody in this class based off of the data set who did not complete high school and who is between the 24 and 34, 25 and 34 age limit, who has completed college, which is 4 or more years, and who is between the age limit of 35 to 54. So these are certain ways of visualizing categorical data. As we move on to the next piece of the puzzle, in the next video, we will start looking into managing quantitative data. This is where it becomes a lot more interesting because it really offers a wide range of analytics. And so this is where we start looking at charting quantitative data. We'll look into some of the bar charts, box plots, and so on and so forth as we move on.